IPv4 addresses, 32 bits, easy representation. IPv6 addresses, 128 bits, not quite so easy. IPv4, dotted decimal, just regular numbers. IPv6, numbers and letters. Yeah, I don't want to say numbers and letters. They're not letters. It is A, B, C, D, E, and F, but those are not letters. They're numbers because it's a hexadecimal value. We need 16 unique numbers. Sometimes people say, is it capital A or lowercase a? I'd say it's not an uppercase or lowercase. It's a number. Have you ever heard of an uppercase 2? Probably not. Being as long as that address is, we like to have ways that we can represent it more efficiently. So we're going to take a look at the IPv6 address representation and how to make it efficient. So here's an IPv6 address that I've just thrown up here, kind of made this up, 2001486000000001 012A1500. Again, long and cumbersome. Is there some way we can make this look a little bit more efficient? Maybe we'll do a quick little blurb into what we're looking at here. So if I look at this first portion, this 20014860, that's the global address space. This one actually belongs to Google, so this is a representation of Google. The next 16 bits in here, 32 bits in here, is the subnets that Google defines. So these are Google's, but these are Google's, again, we don't really call them subnets, we'll call them networks, but these are network bits, so this is the number of subnets that Google can have. How many subnets can Google have? Well, this is 4, 8, 12, 16, and 32. This is 32 bits. So 2 raised to the 32, it's 4.3 billion. So Google now has the ability with IPv6 to have 4.3 billion subnets. The last portion of this address space here is the host portion. This is the unique host values. So Google has what, 64 bits of host portion. So how many addresses can Google have on each subnet? 2 to the 64th. Somewhere around, I think this is 18.6 quintillion. I might be off there a little bit, but it's a huge, huge number. So again, the span of IPv6 means we're really not going to run out of addresses in the near future. So we're using IPv6 because it gives us all the flexibility that we need, where, you know, the folks that came up with our addressing space in the first place with the early RFCs back in the late 60s, early 70s, when IPRFC was actually adopted in 1981. So those folks saw that we had 4.3 billion addresses and said, wow, that's plenty. Well, they were only looking at 1 or 2 machines in each establishment having it. They weren't looking at people having 20 addresses in their house. So we had to come up with a bigger space. Again, to make this more efficient, what are the rules? Well, one of the rules is that we don't have to use any preceding zeros. We can actually just drop them. Preceding meaning at the beginning of every superoctet. That's what I call it, a superoctet. Again, I think they're probably going to call it a hextet at some point. This hextet is this one representation of 4 nibbles, a hextet. That's probably the terminology that we'll end up hearing down here. So in the hextet, we can eliminate any preceding zeros. So if I had 0, 1, 2, 5, that 0 can go away and I can just use the 1, 2, 5, and that works fine for me. So up here, what can I get rid of in 2001? I can't get rid of anything. It's got to stay. I don't have any preceding zeros. How about 4860? That's got to stay too. What about 0000? I can get rid of the 3 preceding zeros. So I can say colon 0 colon. What about 0001? Again, I can get rid of the 3 preceding zeros, so I can just call it colon 1. What about 0000? Yeah, we saw that from before. 000, yep, we saw that from before as well. What about 012A? I can get rid of the preceding 0, 12A. What about 1500? Got to have this whole thing. I cannot get rid of trailing zeros, so that whole piece has to stay. So that is one more clear, more clean representation of an IPv6 address. Is there another thing we can do? They came up with one more rule, and that is I can replace group or groups of zeros with a double colon. So when I look up here, I've got a single group here of zeros. I've got two groups here of double zeros. So one of these two groups I can replace with a double colon. So it would be more efficient for me to get rid of this group right here. So I'll replace this with just a double colon. So it turns into 2001 colon 4860 colon 1 colon colon 12A colon 1500. That one double colon right there is a variable, which means fill this with zeros until you get to 128 bits. Whoops. I actually missed something here, didn't I? For those of you following along, what's going on here? What did I miss? This 0 is missing. I put a colon 1 in here without the colon 0. So let me go back. Let me just go back and redo that whole piece. Not really a big deal. Again, it's why we go back and we look at and we evaluate what we're doing. So it's 2001 colon 4860. I cannot get rid of this 0 because I'm going to get rid of the other ones. Colon 1 colon colon 12A colon 1500. So in my first representation, for those of you who have it still written down if you want to look, I had left that 0 out. When you put it in, it wouldn't have thrown an error anywhere as far as the syntax goes because this double colon allowed me to fill in all those extra zeros, but they clearly would have been in the wrong spot. Now that we go back and we look at this, this double colon is that variable. You can only have one variable. I cannot, and again, what I could not do is I could not remove this 0 and have two double colons. If they're variables, how do I know how many zeros to put in each one? So you can't have two double colons in an address. You can only have one. And the most efficient way to represent this is right there. IPv6, efficient representation.